So again, we're talking about inference, but this time it's not proportions, it's counts. So mu, sigma, x bar, that kind of stuff is what we start looking for counts. But we don't know sigma or mu. This is a real problem. So the other day, I said that if we don't know P, the population proportion, what do we do to substitute? Yeah.
Replace it with P hat.
Exactly. So if we don't know sigma, what do you think we might replace that with? You're the second person to suggest that. What does sigma correspond to for samples? S of x, right? S or S of x. Yeah. So we use S of x as a replacement. To calculate the margin of error. The problem is when we use S of x, it turns out that it doesn't really work to use table A. But we can't use table A. It's not entirely normal. Or for whatever reason that is probably deeper than my understanding of statistics, the values don't quite line up the same. They just don't. My understanding history of this was they were using table A, but they kept noticing that their numbers weren't quite right. So somebody came up with this other table that does work. It's adjusted for the use of the standard deviation Sx. So we use the t distribution table I can't write table without not putting the L in today for some reason. So if I do taba, that's table. So we use the t distribution when substituting Sx for an unknown sigma. And think about it, really. How often in the real world are we really going to know the mean of a population or the standard deviation of that population? In the real world, I'm guessing it's almost never. Okay? Unless your population's very small, those are values you probably just aren't going to know. Unless you've done many samples. So to estimate a population mean, use x bar. X bar we can get from any sample, right? We can one var stats or whatever if we have a sample of data. Plus or minus, this is a new one, t star. So this is the value that we take off the t-distribution table. And the star indicates, well, that it's going to be the plus or minus, right? At least that's how I see it. Otherwise, it's just t. Times Sx over the square root of n. I think you're going to like this if you're 12 like I am. This piece right here, this isn't standard deviation. Or hang on, back up. I went too far. Sorry. Just this part right here. This isn't standard deviation. This is standard error of x bar. Right? Come on. It's never too early for a little joke. Come on. See, and what the cool thing is you guys are getting close to, I mean, that's true. That's what that is. You guys are getting close to where I can actually start pulling up stats memes. Yes, I know there are nerdy stats memes, but some of them are pretty good. Some of them are pretty good. Yeah. my very excellent Spanish teacher in high school said you understand a language when you can get the humor in that language. And it's true of any language, right? Stats is just another language. So, yeah. So this is the standard error of the sample mean. And come on. Really? You want to be 12. Trust me on this. You want to be 12. So, well, okay. And maybe Ben needs to be 13. I don't know. So my son a little while ago, he's going to be 14 pretty soon, and an issue arose, and I'm like, dude, just be 12. Be 12. Just be 12 for a little while. And I said, and when you're 13, be 12. Okay? And when you're 14, be 12. And where I was going with that is, when you're 50, be 12. I mean, really. When you're like, how much?
52.
Well, I'm pretty close. So, be 12. Okay? Life is more fun when you're 12 than it is when you're... Okay, so that's my attempt at a normal curve here, a normal-ish. So we have x bar in our middle. So this is x bar plus t star times sx over the square root of n. Let me zoom in on that a little bit because I'm sorry I'm writing that so small. I'm trying to, for the first time in my life, I'm trying to conserve paper. I don't know why. Okay. And x bar minus t star sx over square root of n. So what the t star sx over the square root of n is, that's your margin of error. Yeah, I know, you can't see. It wasn't intended for your eyes. Thanks, though. What is t star sx over root n? That's margin of error. So it's doing exactly what we did with the proportions in the last thing. It's just doing it with counts. And of course, we still have conditions. We'll talk about those next. And then we need to look through some problems because I don't want you to be completely left out in the rain on this one. Because I would be willing to bet as much as a taco dinner that you'll have a problem like this on the AP test that's free response. Either proportion or count, but it's going to be, I'd almost bet you'll use this on the AP test. Okay? Well, I would bet. I wouldn't bet my life, but I'd bet a taco dinner, which is almost my life.
Yeah, but it has to be on Tuesday. I ain't taking any tacos any day other than Tuesday.
You only eat tacos on Tuesday?
Taco Tuesday.
Well, yeah, I agree. Tuesday's the best day for tacos, but I think, is there really a bad time for tacos?
No, there's not.
I didn't think so. Like when I was a kid, my mom would make, we made tacos out of our pancakes. I mean, yeah.
Tacos? Oh, that sounds so good.
No, yeah, you take the pancake and you put a little butter on it, and instead of syrup, you put like either powdered sugar or brown sugar, and you roll it up. Oh, yeah. Doesn't get any better than that. Okay, on the offhand chance that sigma is given, and you do get problems like this on occasion, we use the inference formula, x bar plus or minus. Now it's not t anymore because we have sigma. T is when you do not know sigma, so z star sigma over root n. And you may run across a problem or two like that in the assignment. So you have to decide, do I know the standard deviation, or do I have to calculate, or did somebody have to calculate the standard deviation? That's the difference between your z and your t. Okay? Conditions. Has to be random sampling of some sort. You can say SRS, that's fine. And you have to, when you go through your conditions, you have to say why. Either it's reasonable to assume, and we haven't really run across a problem like that yet, but we will. Or it's given, generally. Or the 10% rule. 10% of the population has to be larger than the sample. This has to deal with independence. One of these days soon, if we have some time, I'll share with you an email that I sent to our union head guy. He's taking a survey of all teachers, and I'm like, you got a problem with that? Yeah, that's a problem. You can't do that. Yeah, that's a census, and unless you get everybody to participate, your data will be junk. And I tried to explain it to him. And then I proceeded not to take the survey. Because I knew it was going to be junk, right? That's right. That's right. So don't mess with me. But it deals exactly on the kind of stuff we're talking about here. It's just totally appropriate for what we're talking about now. So n is greater than or equal to 30. Yeah, in the email, he basically said in his response to me the first time, I said, hey, I think you've got some problems here, you know, if you're concerned. And he responded, he says, yeah, I know our sampling, we don't really have that large of a sample. It's like there's 2,200 people that they've questioned and they've gotten like 350. And I said, no, the problem is you've got too many people already, you know. It's an issue. It doesn't meet the 10% rule. So normal, n is greater than or equal to 30 by CLT, or given. In the case of given, or the parent population is normal. When sigma is given. Remember, if the parent population is normal, we don't care what the sample size is. It could be anything. If we don't know if it's normal, n has to be greater than or equal to 30. But if we're not given sigma, I detect a problem in my notes that I wrote the other day here. Is no strong skew. A little skew is okay in the parent. When SX is used. Actually, I don't really know that I do detect the problem now. Let's see it. So, if you're using the standard deviation that's calculated, you really only need a very roughly normal pattern. If it even looks like it's kind of heading in a normal sort of way, and there's not some massive skew to it, you can use your T star values. So it's less picky than this guy here. This is more picky about it being normal than when you use this SX. Does that make sense? So give yourself a little bit more leeway to call things normal that you might not normally go, oh yeah, that's not normal. I could kind of see where it's heading normal. Okay, the last thing that you need to know, T star values. This is an afterthought that probably shouldn't have been an afterthought. T star values must use degrees of freedom. Don't worry, this is easy. That's df, and how you calculate df is you take 1 from n minus 1. What the degrees of freedom does is it makes your confidence interval ever so slightly less wide. It's kind of like adding an extra measure of security to make sure that you're capturing, actually not less wide, it would be more wide. It's actually making it a little bit more wider so that you're not missing something by a small decimal value or something. So the degrees of freedom just ekes it out just a tad more. Right, so let's look at a problem. Let's look at number 61. You all with me? Okay. So 61 just asks us to practice using the table. Get there. Let's see, that's on page 542, 541. And this asks us to just evaluate some information that's given on degrees of freedom here and all that. A is a 95% confidence interval based on n equals 10 observations. Okay, so what's the degrees of freedom if n equals 10? 9. That is something you need to write down for every problem that you do where you use t. df equals and then whatever n minus 1 is. So that tells the grader that you understand the degrees of freedom. So let's look at this guy. This is actually even easier, quite a bit easier, I think, than table A. It's only one-sided. Here are your degrees of freedom. Something that I didn't add in the notes is you always round down. So you might even put that here, always round down. At the top, you have upper tail probability, but we're not going to use that yet. That comes in a little bit later. Look at the bottom. Confidence level. I mean, it's spelled out right there. So these are your confidence levels, and these are the common ones. But the most common are the ones that I've given you, 90, 95, and 99. Most of the time you're going to be looking at those. But if you wanted a 96 or a 98 or even something wider than 99%, you've got some good options here. So to find the value that this problem is looking for, I just go to 95% and I go up until I find 9. See, where am I at? Make sure I'm in the right column there. 2.262 it looks like. That's it. So t equals 2.262. Oh, sorry. There we go. Pulled it straight off of the table. So B says 99%, n equals 20. So degrees of freedom, 19, right? And we'll just pull T. Let's see. So I go to my 99%, and I go to 19. 2.861 it looks like. Okay. And let's see. C, 90% confidence. I've got a random sample of 77. Degrees of freedom equals 76. Now I got a problem here. Oh, here on the values, we jump from 60 to 80. So do I use the 80 or do I use the 60? 60. Good. We always round down. It doesn't matter what it is. So in that case, it's going to be 1.671. But why do we round down, and how much difference does it make? Almost none at all, because 1.671 is for 60. Look how much it is for 80. It's only like 3 thousandths bigger. So whenever you're rounding down, remember you're making that just a tad bit wider. Degrees of freedom does that, and by such a small amount that it's not really significant. So what if I gave you something where I said n is 999? You'd use 100, right? The only time you'd actually use 1,000, I think they just kind of put this in here sort of as a boundary for anything bigger than that. That's what the Z star is. Anything bigger than that, I don't know why they have Z there, but maybe at this point it actually mirrors. Oh, it does. These are actually Z star values. At that point, the table A and the table C have come together as far as they're the same. So the only time you'd ever use this 1,000 is if your sample size was exactly 1,001. That'd be the only time. So they kind of use it as, I think, a barrier between the T values and the Z values. Does that make sense? So anything from 101 to 999, you use 100. So always round down. And look, the difference, it's minuscule, right? It's there. It's a little bit bigger, but it's not enough to cause any problems in your calculations. Okay, always round down. So what did we have here? What did we get for T on that one? 671? Yeah, cool, thank you. All right, let's look at number 65. I didn't actually write anything down for 65. We're checking conditions here. Let's just go through these, see if we've met our conditions. A, how much time do students at your school spend on the internet? You collect data from the 32 members of your AP statistics class and calculate the mean amount of time that these students spent on the internet yesterday. Okay, SRS. Is this an SRS? No. So we break that condition right off. So we've not met the conditions in A. Looking at B. Is the real estate market heating up? To estimate the mean sales price, a realtor in a large city randomly selected 100 home sales from the previous 6 months in her city. These sales prices are displayed in the box plot. Okay. Is it a random sample? Okay, so SRS is met. So SRS is okay. How about the 10% rule? She's selected 100 homes. That would mean that they would have had to have sold more than 1,000 homes in this market
In a large city.
in 6 months. In a large city. That's true. Does that seem like we've met the 10% rule, do you think? Okay. Usually if they say a large something, this makes me a little nervous. I mean, 1,000 home sales in 6 months, I don't know, I'm not a realtor, but that seems like a lot, but maybe it's not in a really hot market. Maybe it's not. So let's say the 10% rule is met. Are we normal? The only thing we have is this box and whisker plot to look at to decide if there's any normality there at all. And box and whisker doesn't really tell you shape all that well, but what I would say is that our quartiles are fairly close in size. There's no massive skew in that, except we do have some outliers. And the outliers actually are the problem here. So I think we have not met the conditions here because of the outliers as much as anything else. If she kicked the outliers out, then I think maybe, you know, you'd be down to 95 and possibly you'd be okay. But those outliers create quite a skew. And that's it for 65, is just the two. So I don't believe we've met it on in either situation. If I was answering this question for an AP test question, though, to be perfectly honest with you, I'd say if we eliminate the outliers, then it's reasonable. We have there's no strong skew here. We can work with a confidence interval. That's where I would go with that. But given what they've given us, I'd say it's not normal. It doesn't meet the condition. Okay, without doing that. All right, and the last one that I wanted to go through was number 71. I'm a little worried about 73, but I like 71 for another reason. Let me just give you a heads up on 73 real quick. You actually have some data. And so to get a standard deviation of that, make a list, do one var stats, then you'll have SX, you'll have X bar, and those would be the things that you'd need for that. Okay, and N, you'd get all that from one bar stats. So let's look at 71. 71 says America's favorite cookie, and who doesn't have, I mean really, if you don't eat cookies and they're not like your absolute favorite thing, that's great because they are my absolute favorite thing, and that leaves more for me. Ann and Tori wanted to estimate the average weight of an Oreo cookie to determine if it was less than advertised. Another disadvantage of having a phone bank, right? Okay. Right. So what we're given is that 3 cookies is 34 grams. That's the claim that the company makes. And what they did is they selected a random sample of 36 cookies, and they weighed each cookie. The mean weight, X bar, was 11.3921 grams. And it contained a standard deviation of 0.0817 grams. Construct and interpret a 90% confidence interval. Excuse me. Okay, first thing, we need to cover conditions. SRS or random? That's there, that's given, right? If you're doing your own work, a check is fine, but if you're doing something for anybody else, you need to say given. 10% rule. Is it reasonable to assume that 10% of all cookies, all Oreos, is greater than 36? Not only is it reasonable to assume, I count on it from my life, okay? Right? Oreos are life. It's reasonable to assume. All right, and is it normal? Yeah, by the central limit theorem, right? 36 is greater than or equal to 30, so normal. You have to say by the CLT. You can't just say normal. That's assuming that the person that you're talking to knows about the central limit theorem and that they understand that you know it. But that's too much of an assumption to make. All right, so we can now calculate this. So what I'm going to do is, since we have Sx, I need the t star value for this, or the t value. Let's look that up. So my sample size is 36. What's my degrees of freedom? 35. Good. See, I told you that was easy, right? So then I'm 90% confidence interval. I'm actually going to do something fun here. I'm going to actually highlight all my 90s, my 95s, and my 99s. What's that? Those are the most common ones. So if I go to 36, I'm 35, I mean, I guess it doesn't really matter. I got to jump down to 30, which makes that 1.697. And now I'm good to go. So this is going to be X bar, 11.3921, plus or minus T star, 1.697, times the standard deviation, 0.0817, divided by not the degrees of freedom, but the actual n value, but the square root of that. Square root of 36. So that's just 6. So like the other day, what I said was I like to do the minus one first because I get the smaller number value first. So I'm going to go 11.3921 minus 1.697. Put the square root in. I don't really need any parentheses in this case. The order of operations takes care of me. Oh, wait a minute. I take that back. I just made a mistake. Times 0.0817 divided by square root of 36, which is just 6. And I am a little concerned about that. I wonder if I do need some parentheses in there. Let's see. No, it looks like it's fine. So 11.369 to, make sure you're rounding correctly, and all I'm going to do is change the minus to a plus. $11.415. So now we have to answer in context. even if it's just you, we say we, because we're nice people and we give everybody credit in this class apparently, in stats, okay? We are 90% confident the true mean how do I know it's mean and not proportion? Because of the X bar here. The true mean weight of an Oreo is between 11.369 and 11.415 grams. Calculation doesn't take long, it's all the prep work for that. So give these a try. I'll come around and help out. I think a couple of you still need to get your test, so